Welcome to Inverkenny Junction. Today we're going to talk about soldering and wiring. Soldering and wiring are skills you'll obviously need to learn as part of constructing your model railway. So this video is really aimed at someone completely new to soldering, but there's also some hints and tips in here which someone who's been soldering for a while might also find useful. So I've been an electronics engineer for the last 40 years and virtually soldered every day. I think what prompted me to make this video was two factors. On one hand, it amazes me how technically competent a lot of railway modelers are when it comes to electronics, soldering and wiring. For example, check out the Perth South YouTube channel. This must be one of the most technically advanced layouts I've ever seen, with full block detection signalling replicating the real thing. The amount of wiring and electronics on this layout is quite amazing. However, at the other end of the scale, you've got a lot of really popular model railway YouTube channels showing you how to do soldering and wiring who quite clearly are not qualified to do so. They tend to show a lot of misleading information and bad practices. Whilst this might work initially, it can lead to faults and problems later down the line. Wiring a large DCC layout can be time-consuming and complex. So if you employ good practices from the start, you'll not only save time, but you'll minimise faults in years to come. With good wiring practices, you'll also make it easier to find those faults when they do occur. So let's start with a soldering iron. We use Weller soldering iron stations, which are about £400 each. You don't need to spend this much for hobby use, but we're obviously going to have good quality kit because we use our soldering irons every day. So if you're choosing a soldering iron for hobby use, there's a couple of key things to look out for. The cheaper irons don't have a power supply and are connected directly to the mains. These are okay for wiring, but if you try and solder semiconductors, you'll just blow them up. With these irons, as the thermostat switches the iron on and off, it produces really high voltage mains spikes. This is enough to damage or degrade sensitive semiconductors. So if you intend to solder anything that has some electronics connected to it, you really need a low voltage iron. So check this on the soldering iron spec. They normally run off of 24 or 48 volt DC, and you can normally spot them because they have a separate power supply. The second thing to look out for is temperature control. Again, this is not so critical if you're just doing wiring, but if you're soldering electronics, temperature control is essential. Also look for a soldering iron that has tips that are interchangeable easily. You'll need to change the tip regularly as they do wear out. You'll also want a smaller tip for electronics and a larger tip for soldering track and heavy gauge wiring. So when you order up a soldering iron, make sure you get a selection of tips with it. If you can't buy spare tips, don't buy the iron. So the next thing to talk about is solder. You've basically got two types, leaded and lead-free. They're both what's called a multi-core solder, where you've got multiple cores of flux embedded in the solder. You can of course buy solder with no flux in it, but that's really for specialist applications such as soldering radiator pipes where you'd add your own flux. So up until 1995 we just had leaded solder. This is typically 40% lead and 60% tin. But in 1995, the bureaucrats, in their wisdom, decided that the levels of lead in waste printed circuit boards were a hazard to the environment. So they brought in the RoHS directive, which banned lead in solder. There were exemptions for military and medical equipment, and that there alone tells you all you need to know about lead-free soldering. Soldering lead-free is difficult, and the joints tend to be unreliable. This ironically led to a huge increase in waste electronic equipment as things just didn't last as long as they used to. The quality and reliability of commercial lead-free soldering has now improved vastly, so equipment reliability is now a lot better than it was. So from the hobby perspective, just solder with lead. Lead solder is still readily available and it's much easier. If you're soldering lead-free, for example, you virtually have to change your tip almost every day. So this sort of brings us on to health and safety. Lead is obviously toxic to the body and there's a perception that it's quite dangerous. However, the only way lead gets into the body from soldering is if you're soldering and don't wash your hands and then eat something, you typically ingest some lead. So always wash your hands thoroughly when you're finished. So the fumes from soldering are from the flux. With normal lead solder, this is typically just an irritant to the eyes and airways. The best way to keep the flux fumes away from you when you're soldering is to just use a fan to gently blow the fumes away. We use this fan heater, which has got a fan only setting, which is ideal. Going back to lead-free solder, the flux used is actually toxic. The cocktail of chemicals they've had to add to the flux in order to make it solder is actually quite lethal. This is your typical example of bureaucrats making legislation about things they know nothing about, which actually makes the work environment more toxic than it was before. So again, another reason to avoid unleaded solder. So let's begin with soldering two wires together. So the basic tools you'll need are a pair of side cutters, a pair of long nose pliers is useful, and some wire strippers. Wire strippers come in two flavours, the manual wire strippers and the automatic version. With the manual wire strippers, you adjust the cut depth with the screw. This has to be adjusted every time you change wire size. To set it, do a few test strips. If the cut's not set deep enough, it'll be difficult to strip. If it's too deep, you'll cut into some of the strands of wire. Once you've got it set right, you can tighten the lock nut. Manual wire strippers are a bit tedious if you're doing a lot of wiring, so to get around the problem, we use automatic wire strippers. With these, just put the wire in like so, give it a squeeze, and the wire should strip. If it doesn't strip, you can adjust the cut depth here. And there's even a little slider in there to set the strip length. You're much less likely to cut into the cores of the wire with automatic wire strippers, so that's why they're the preferred option. So once you've stripped the ends of your wires, you want to give them a bit of a twist. This helps to stop any loose strands coming astray when you solder the joint and causing a short on adjacent wiring. So before we solder the two wires together, we need to do what's called tinning the wires. So first of all, we put a bit of solder on the tip. So first put the soldering iron tip on the wire and then add the solder. You really want to be aiming to do this within a couple of seconds, otherwise you'll melt the insulation. If it seems to be taking you longer than this, it's probably because your soldering iron temperature is too low. You want to aim to keep your soldering iron temperature as low as you can get away with. If your soldering iron temperature is too hot, you'll see the flux will smoke and burn off very fast, and the tip will go a sort of straw colour, and the solder won't look shiny anymore. If your soldering iron's got a temperature display, you're looking for around 340 to about 380 centigrade. So generally a bit lower for soldering printed circuit boards and semiconductors, and a bit higher for wiring. So when you've finished, clean the tip on the sponge, which should be kept moist with water. And then, which is the most important bit, put some solder on it before putting it back in the holder. If you clean it on the sponge and then put it straight away in the holder without putting any solder on the tip, you'll just burn the tip out in no time, as you're basically just putting water on a hot metal surface which oxidises it, destroys the plating, and means you're going to have a new tip in no time at all. The best habit to get into is to clean the tip before you solder and then tin the iron, and not clean it when you put it back in the holder. So once we've got the ends of our two wires tinned, we can look at soldering them together. There's basically three types of joints you can do here: a lap joint, a wrap joint, and a hook joint. The lap joint is the easiest and the best one to use if you're likely to want to separate the two wires at a later date. So for the lap joint, even if the wire's already tinned, put a bit of solder on the end of each wire, a little bit of solder on the end of your iron, and then bring the two together with the iron. As long as you put solder on the tip of the iron and the two wires beforehand, you don't need to add any extra solder. So here it's probably worth talking about the so-called dry joint. This is where you've made a solder joint with not enough flux. So instead of the joint having a nice shiny appearance, it looks very dull. These dry joints can often fracture over time and so become unreliable. Easiest way to prevent the dry joint is to solder fast and put fresh solder on each wire and a tip before soldering. You won't go wrong then. The fiddly thing with doing the lap joint is holding the two wires. I've sort of developed this technique over the years where I hold the two wires in one hand and then my other hand is free to use the soldering iron. An alternative is to use a pair of pliers with an elastic band around the handles just to hold one of the wires. However, there will be situations where neither of these techniques will work. This is normally where you're trying to solder two wires in a real inaccessible location. Underneath a baseboard is an obvious example. This is where we might use the wrap joint. For the wrap joint, strip both ends of the two wires to be joined, twist them together, and then they're ready for soldering. This means you don't have to hold the two wires together, so you can have the soldering iron in one hand and the solder in another. The only downside is the wires are a little bit more difficult to get apart should you need to separate them later on. The final joint we'll look at is the hook joint. This is only really used where the wiring is likely to get hot. You might use this, for example, to join two power resistors which get hot, or in wiring that's required to have a fire rating. So for the hook joint, first strip the two wires. Then tin both ends of the wires. Then use the pliers to make a hook on the end of each tinned wire. Then hook the two ends together and squeeze them together with the pliers. You'll see now the two wires are fairly solidly connected even before we've soldered them. So we can then solder the joint and then that's all done. You probably wouldn't use the hook joint in a model railway application, but it's worth showing you here as I was showing you the two other joints. So now we've soldered the wires, we'll look at various ways of sleeving the joint. If we start with the lap joint, if you remember, this was a joint where we typically use where we might want to separate the wires at a later date. The simplest way to sleeve this type of joint is with silicone rubber sleeving. This is available on a reel in various diameters and you can simply just cut off the length you need. Then just slide it over the wire till it's in the correct position. The advantage of this sleeving is you can simply slide it back off if you need to disconnect the wires at a later date. Another solution for sleeving is heat shrink tubing. This is available in a variety of diameters and colours. So again, just cut off the length you need. You probably want at least 10mm either side of the joint to be safe. Then just slide it over the wire till it's in the correct position. I've seen a lot of videos on YouTube where people then attempt to shrink it down with a soldering iron. Do not do this. This is really bad practice as inevitably you get bits of solder stuck to the heat shrink tubing and sooner or later they come off and cause shorts and get into places you really don't want solder splashes. The correct way to shrink down the heat shrink tubing is with a heat gun. We use this battery powered Makita heat gun, but you can also use a mains powered version. These are a bit cheaper and generally sold as paint stripping guns. A battery powered heat gun is about £100, but the mains one you can normally pick them up for £30 or £40. Main reason we use a battery heat gun is to minimise mains load. Our whole factory runs off of inverters and a battery with solar charging. We're in a remote part of Scotland, so in the winter the power can be off as much as it's on, so it's essential we have our own supply. So keep the heat gun moving when you're shrinking the tubing, as you could melt the insulation if you kept the heat on one spot for too long. So for the wrap joint, again, cut a piece of heat shrink tubing around 1 inch long. Place this over the end of the wire, and you want about 5 to 10 millimeters protruding beyond the end of the wire. Once it's shrunk down, give the end of the tubing a little squeeze between the fingers. This seals up the end of the tubing. So for the hook joint, the procedure's the same as for the lap joint. You might have to use a slightly larger diameter of heat shrink tubing, as the solder joint is obviously a bit larger. You can't use the rubber sleeving for the hook or the wrap joint. So if you don't have access to heat shrink tubing or a heat gun, use some insulation tape. The use of insulation tape is generally considered bad practice, but if that's all you've got, it's obviously better than nothing. So thanks for watching the video. If you enjoyed it, please like and subscribe. In part 2 of this video, we'll look at different wire types, and more specifically on how to wire up your layout and add the dropper wires.